Okay, so this lesson we're going to discuss exponential growth and exponential decay curves. So take a look at these two things. They're probably in your guided notes somewhere. Um, look at the equation y equals a times b to the x. So when you look at the equation, if the b is called the growth factor, the B is called the growth factor. And if that's bigger than 1, you have exponential growth. If B is between 0 and 1, you have decay. Now, that's what these graphs look like. You can see the two differences in them um, real easily here. The big thing about A is for both, whether it's growth or decay, A is actually the initial amount when you start with anything, or I like to think of it graphically, that's y-intercept. So the y-intercept is always 0, comma A when you're dealing with exponential growth or exponential decay. Hopefully you get what I'm talking about, because here's the first problem. So since 2005, the amount of money spent at the restaurant in the United States has increased about 7% each year. And in 2005, about 6 billion, 360 billion dollars was spent at restaurants. Okay, so um, if the trend continues, about how much will be spent at the restaurant in 2015. Now, this is obviously old, but you go based off of 2005. What does the expression represent the equivalent monthly increase of spending at U.S. restaurants in 2005? So, what I like to think about is the thing is, it says it increased by a percentage. It increased by a percentage. So, since it increased by 7%, it maintained 100%. So, since it increased by 7%, it maintained 100%. So, I have a equation like y equals a times b to the x. A is the initial start. So A would be 360 billion. So 360 times 1.07, and I take that to the x. That's what I'm going to use. Now, what I'm going to do is I'm going to figure out how many years is it from 2005 to 2015. That's 10. So I'm going to do 360 times 1.07 to the 10th power. So let's do that in our calculator real quick. So I'm going to open up this calculator. Hold on, let it load up. So we're going to go ahead and do in our calculator. In our calculator, we're going to go ahead and take 300. Well, I'm going to do 1.07, 1.07, and I'm going to go to the power of 10, I believe, right? To the power of 10. I'm going to move out of there and I'm going to times that by 360, I think, right? 360. So I get about 708.17. So I'd say about $708 billion. In this case, I'm going to round, but 708.17 billion dollars. Now, if you think about this, what is an expression that represents the equivalent monthly increase of spending at U.S. restaurants in 2005? Well, with this, you kind of got to think of it like this one. You got to think of it as you could just do. Well, they want to do it in monthly, so you want to take it and convert it into months instead of years, right? So what you could do is there's 12 months in a year. So you could say it would be um, 1 point. You do the same exact thing, but it'd be 360 times 1.07 times x divided by 12, because that's years. So no, hang on, no, it'd be 12. I'm sorry, it wouldn't be divided by 12. It'd be 12 times x for months. If that makes sense. If it's 3 months, it would be no. Hang on. If it's 3 months, you're going to take the months and divide it by 12. That's right. So it's going to be divided by 12. So 360 times 1.07 times x divided by 12. That divided by 12 converts however months it is into a year. So if it's 3 months, it's 3 divided by 12, if that makes sense. All right. Another application is what we call compound interest. And this right here looks kind of like y equals a times b to the x. Now I want to explain what each one of these things represents. P is your principal. P is your principal. That's your starting money. R is your rate as a decimal. So if it's a percentage, you turn it into a decimal. N is number of times compounded. So if it's quarterly, it's 4. If it's monthly, it's 12. If it's semi-yearly, it's 2. And T is time in years. This is very important. You will see this again in Algebra 2, and we might mess with it a little bit in this class. So here's an example of it. So it says, suppose that when your friend was born, your friend's parents deposited 2 grand into an account that paid 4.5% interest, compounded quarterly. What will the account balance be after 18 years? All right. So for that, what you're going to do is you're going to put in, so using this formula, P, the principal, is 2,000, parentheses, 1 plus the interest rate is 0.045, compounded quarterly. Quarterly means 4 times a year, taken to the 4 times 18 power. Now, do not try to do this all in one clean shot. All right? Do not try to do that all in one clean shot with your calculator. Calculate each part individually. So if you do this, this becomes 2,000, and then inside here I get 1.01125, and 4 times 18 is 72. Then you plug that into your calculator. So you do 1.01125 to the 72nd power, and then you multiply by 2,000, you get $4,475.53 for that 18 years. Okay, so let's look at some exponential decay stuff. All right, this one, it says the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000-meter increase in altitude, the pressure decreases 11.5%. What is the approximate pressure and altitude of 3,000 meters? So it doesn't matter if you don't know what a kilopascal is. The fact is that it says decreases. So you got y equals a times b to the x. So do we have a starting level? I believe our starting level was 101, right? Right? 101 kilopascals, and b to the x. It's just going to go to the x, but b, I guess if you're losing 11.5%, you're actually keeping 88.5%, so that's 0.885. Now there's our equation. Now we have to figure out, well, if every 1,000-meter increase, so X stands for 1,000-meter increase, so going from 1,000 to 3,000, how many is that? Well, that's 3, so you're just going to do 101 times 0.885 to the third power. So plug that into your calculator, do 0.885 to the third power, times it by 101, and you get 70, is approximately 70 kilopascals is where you're at. Hopefully that helps you and that makes some sense on exponential growth and decay. And I will see you in class tomorrow. And may the force be with you.